Dear students, we have already completed the second unit of Topology 2, and today I am going to start with the unit 3. Actually, we start with the Urysohn's lemma. The first section is a Urysohn's lemma and the Tietz extension theorem. And we first have to discuss the Urysohn's lemma. Before coming to Urysohn's lemma, or before giving the theorem, I am going to introduce dyadic numbers. That is the first definition. Definition dyadic number. What do you mean by dyadic number? A dyadic number is a number that can be expressed as the quotient of two integers where the denominator is a power of 2. Quotient of two integers where the denominator is a power of 2. That is, it is of the form m by 2 raised to n. That's what is given in the first remark. Every dyadic number in I equal to 0, 1, close to 0, 1 can be written in the form m divided by 2 raised to n, where m equal to 0, 1, 2, etc. 2 raised to n. And n is an element of n union set 0. The set of all dyadic numbers in I equal to 0, 1, close to 0, 1 is denoted by capital P, and P is countable. Moreover, the dyadic numbers in or P minus at 0 can be ordered as below. As follows it is given, that is P1 is 1 by 2 only, 1 by 2. What is the order P2? P2, that is 1 by 2 square, that is 1 by 4. Next coming 3 by 4. Similarly, what is P3? 1 by 2q, that is 1 by 2 raised to 3. 1 by 8. Then next 3 by 8. Next 5 by 8. Next 7 by 8. And P4 is actually same way 1 by 2 raised to 4, that is 1 by 16 onwards. 1 by 16, then 3 by 16, 5 by 16, 7 by 16, 9 by 16, 11 by 16, 13 by 16, and finally 15 by 16. That is the ordering. Clearly P is dense in I, or P bar equal to I. We can discuss a theorem that statement is given here, which is essential for proving the Urysohn's lemma. I am not giving the proof of it, only statement is giving. The statement is that X2 be a topological space and capital D be a dense subset of I. Suppose that for each T in D, there exists an open set UT in capital X such that first one, if T1 is less than T2, then U T1 bar is subset or equal to U T2. Second is X is the union of UTs for T in D, and define F from X to I by F of X equal to the greatest lower bound GLB of T in D such that X in UT for each X in X, then F is continuous. This is the first theorem. And second theorem that we already discussed in the previous chapter, previous section, that is in normality. The theorem statement is a T1 space X2 is normal if and only for each closed subset C of X and each open set U such that C subset or equal to U. Then there is an open set capital V such that C subset or equal to V and V bar is subset or equal to U. Now we are in a position to give the statement of Urysohn's lemma. The question will be state and prove Urysohn's lemma. And this is the first version, that is we are discussing about F from X to I we are discussing here. And when we are discussing F from X to an arbitrary interval AB, that's also possible. That will be given later. So after the proof of the statement it is given, which is a generalized form. Anyway, you can discuss both the cases. One is for the closed interval 01, other one is for the closed interval AB, that is generalization of it. Or we can discuss the homeomorphism there, what is going to happen there. That we can discuss later. Okay, first we can do this part. Eurison's lemma statement. A T1 space X2 is normal if and only if for each pair capital A, B of disjoint closed subsets of X, there X is a continuous function f from X to I such that f of X equal to 0 for all X in A and equal to 1 for all X in B. And for all X in A, f of X will be 0. For all X in B, f of X will be 1. Where f is a continuous function from X to the closed interval 0, 1. We can discuss the proof of it. Suppose that X2 is normal, that A and B be two disjoint closed subsets of X. It's also given in the statement that capital P denotes the dyadic numbers in I minus set 0. In I minus set 0. Then it can be ordered as follows, that we discussed earlier. Same way, 1 by 2, then 1 by 4, 3 by 4, 1 by 8, 3 by 8, 5 by 8, 7 by 8, etc. etc. So we have A intersection B equal to 5. This implies A is subset or equal to X minus B, where X minus B is an open set. What X2 is normal. Therefore, by the theorem double star. Actually, earlier I have given two theorems. One is theorem star, second is theorem double star. So the second theorem, that's what theorem double star. There X is an open set. Instead of V, we are taking U half, U1 by 2. U1 by 2 such that A subset or equal to U1 by 2 and U1 by 2 bar is subset or equal to X minus B. You can refer the statement of the theorem same way. Instead of V, we are having U half. That's what the statement we are given now. V is, how it is given, C is subset or equal to V and V bar is subset or equal to U. That's what is given. Instead of U, we are having X minus B, which is the open set, and A is the closed set. So instead of C, A, it is A subset or equal to this V, that is U half, and V bar subset or equal to U there. Instead of U, we are having X minus B. So clubbing these together, we can write A subset or equal to U1 by 2, which is subset or equal to U1 by 2 bar. A is always subset or equal to A bar. Subset or equal to X minus B. Call it as 1. Now A is subset or equal to U1 by 2. This implies that X is an open set to U1 by 4, such that A subset or equal to U1 by 4 and U1 by 4 bar is subset or equal to U1 by 2. Actually, A is subset or equal to U1 by 4, which is subset or equal to U1 by 4 bar, which is subset or equal to U1 by 2. You call it as 2. Again, U1 by 2 bar is subset or equal to X minus B, which implies that X is an open set to U3 by 4, such that U1 by 2 subset or equal to U3 by 4. And U3 by 4 bar is subset or equal to X minus B. Clubbing together, we can write U1 by 2 subset or equal to U3 by 4 subset or equal to U3 by 4 bar, which is subset or equal to X minus B, and the result 3. From 2 and 3, what we can write? A subset or equal to U1 by 4, which is subset or equal to U1 by 4 bar, which is subset or equal to U1 by 2, which is subset or equal to U1 by 2 bar, which is subset or equal to U3 by 4, which is subset or equal to U3 by 4 bar, which is subset or equal to X minus B. Now, A subset or equal to U1 by 4, which implies there exists an open set U1 by 8, such that A subset or equal to U1 by 8 and u1 by 8 bar is subset or equal to u1 by 4. Call it as 4. In a similar way, u1 by 4 bar subset or equal to u1 by 2 implies there is an open set u3 by 8 u3 by 8 such that u1 by 4 bar is subset or equal to u3 by 8, which is subset or equal to u3 by 8 bar, which is subset or equal to u half. The fifth one, u1 by 2 bar is subset or equal to u3 by 4, implies there is an open set u5 by 8 such that u1 by 2 bar subset or equal to u5 by 8 subset or equal to u5 by 8 bar, which is subset or equal to u3 by 4. That is sixth one. Again, u3 by 4 bar subset or equal to x minus b implies there is an open set u7 by 8 such that u3 by 4 bar subset or equal to u7 by 8 subset or equal to u7 by 8 bar, which is subset or equal to x minus b. It is the seventh statement. And clubbing all these, that is from 4, 5, 6 and 7, it follows that a subset or equal to u1 by 8 subset or equal to u1 by 8 bar, which is subset or equal to u1 by 4 subset or equal to u1 by 4 bar subset or equal to u3 by 8 subset or equal to u3 by 8 bar, which is subset or equal to u1 by 2 subset or equal to u1 by 2 bar, which is subset or equal to u5 by 8 subset or equal to u5 by 8 bar subset or equal to u3 by 4 subset or equal to u3 by 4 bar subset or equal to u7 by 8 subset or equal to u7 by 8 bar, which is subset or equal to x minus b. Proceeding like this for each t element of this collection, that is 1 by 2, 1 by 4, 3 by 4, similarly 1 by 8, 3 by 8, 5 by 8, 7 by 8, etc. etc. We have an open set ut satisfying the following. What are the conditions? Should be in order with the theorem star, theorem 1. A t1 less than t2 implies ut1 bar subset or equal to ut2. Put d equal to p union set 1. Singleton set 1 is included. Then u1 equal to capital X, d bar equal to I, and union ut t and d, that's equal to capital X. Then by theorem star, the map f from x to I defined by f of x equal to the greatest lower bound of t and d such that x in ut is continuous. We are taking the cases separately, when what happens when x in a and what happens when x in b. If x in a, then x is in ut for all t, because a is subset or equal to ut for all t. Then what is f of x? GLB of t in d. What is that? 0, because 0 is in d. If x in b, what happens? Then x is not an element of ut for all t in p, because a and b are subsets or x. X in b implies x in x. This implies x is in u1, which is equal to x. Then f of x equal to GLB of 1, it's 1, because x is an element of u1. So we get f of x equal to 0 for all x in a, equal to 1 for all x in b. That is what the result we are getting. So whenever x is normal, we are getting this result. The same way we have to consider the converse case. Conversely, suppose that x2 is a T1 space. For each pair AB of disjoint closed subsets of x, where x is a continuous function f from x to I such that f of x equal to 0 for all x in A, equal to 1 for all x in B. Put u equal to f inverse of 0 half, closed interval 0, open interval half. V equal to f inverse of open interval half and closed interval 1. Then u and v are disjoint open sets in x such that A is subset or equal to u and B is subset or equal to v. So we get x2 is normal by the definition of a normal space. That is what the proof of Urysohn's lemma. Urysohn's lemma we have proved now. And as a part of or as a part of the theorem of as a part of the proof of the theorem, we can also arrive at the following theorem. The question can be asked like this, that is theorem, every normal space is completely regular. How to prove every normal space is completely regular? That is, we can discuss the proof that X2 be a normal space. To prove that X2 is completely regular, let C be a closed subset of X and let a P element of not an element of C. Then C and set P are disjoint closed subsets. Then we can make use of Urysohn's lemma. By Urysohn's lemma, there exists a continuous function f from capital X to I such that f of x equal to 0 for all x in C equal to 1 for all x in set P, singleton set P. Or we can write f of p equal to 1 and f of x equal to 0 for all x in C. That means x2 is completely regular, or their definition of complete regularity is satisfied, or we arrive at the conclusion that every normal space is completely regular. Now we are in a position to discuss the generalized version of Urysohn's lemma, because in the proof of Urysohn's lemma we have already taken f from x to I, that is x to closed interval 0 1. That closed interval 0 1 can be replaced by a general interval, that is what AB, closed interval AB. That's what we are going to discuss in the generalized version of Urysohn's lemma. Statement: a T1 space X2 is normal if and only for each pair AB of disjoint closed subsets X, there exists a continuous function f from X to closed interval AB such that f of x equal to A for all x in A equal to B for all x in B. You can see the proof of it. Suppose that X2 is normal and A and B be disjoint closed subsets of X. Then by Urysohn's lemma, there exists a continuous function h from x to I such that h of x equal to 0 for all x in A equal to 1 for all x in B. And we are defining a new function k from I to, that is a function from, actually k is a homeomorphism we are discussing between closed interval 0 1 and closed interval AB. If such a homeomorphism exists, then we can prove the generalized version. That is what the idea. So define k from I to AB, closed interval AB, by k of t equal to A plus B minus A into t. Then k is a homeomorphism and put f equal to k composite h. Then f is from x to closed interval AB, which is continuous. If x in A, what will happen? What is f of x? K of h of x, k composite h of x, or k of h of x, or k of 0, that is what A. That is f of x equal to A for all x in A. If x in B, f of x equal to k composite h of x, that is k of h of x is equal to k of 1 is equal to A plus B minus A is equal to B, or f of x equal to B for all x in B. Hence, there exists a continuous function f from capital X to closed interval AB such that f of x equal to A for all x in A equal to B for all x in B. Now we are defining h from AB to I. Define h from closed interval AB to I by h of t equal to t minus A divided by B minus A. Then h is a homeomorphism. Put k equal to h composite f. Then k from x to I is continuous. Then k from x to I is continuous. If x in A, k of x equal to h of f of x, which is h of A is equal to 0. That is k of x equal to 0 for all x in A. If x in B, k of x equal to h of f of x, that is h of B is equal to 1, or k of x equal to 1 for all x in B. Then by Urysohn's lemma we get x2 is normal. we get x2 is normal. That is, we are making use of Urysohn's lemma. This is the generalized version of the Urysohn's lemma, or the proof is completed. Thus 8 pages notes are also given here together with this video. You refer the notes properly and listen the video, and any doubts means we can discuss in the next class. That's okay.